So when we talk about internal processes, what are we talking about? So this has to do with the various processes that are occurring within the Earth. All right. So we can look at the structure of the Earth in terms of the compositional layers. And as far as that is concerned, we have the crust, the mantle, and then the core. All right, the crust, the mantle, and the core. So the crust is composed of two components. We have the very thin outer rock. There's a very thin outer rocky shell of the Earth. So we can talk about the continental crust and then the oceanic crust. The continental crust, which is the crust on the land or on the various continents, and the crust beneath the oceans. All right, that is the oceanic crust. The continental crust is thicker and less dense, meaning it has a lower density compared to the continental crust, the oceanic crust. The oceanic crust has a much higher density, all right? And then when we look at the composition of the continental crust, it is mafic to felsic. All right, mafic means dark colored. Mafic means dark colored. So it is mafic to felsic in composition. So dark colored, all right, dark colored. Mafic to felsic in composition. And then the density is not high as compared to the oceanic crust, but it is very thick. And when we talk about the oceanic crust, it is thinner, all right, it's thinner, but with a greater density compared to the continental crust. And then the oceanic crust is generally mafic, meaning it is composed of dark colored minerals. It is dark, mafic in composition. All right, mafic in composition. So that is the difference between the crust beneath the ocean and then the crust on the continent. All right, the continental crust. So that is the difference between the oceanic crust and then the continental crust. Then we can talk about the mantle, which is the next layer. We know as far as the compositional layers are concerned, we have the crust, the mantle, and the core. The mantle is very hot. It's actually a hot solid, but it is capable of flowing slowly over time. It is rich in iron, magnesium, and silicon. All right. Then we can talk about the core. So the core, there are two parts. We have the outer core and the inner core. So the outer core is made up of essentially molten iron and nickel, whereas the inner core is made up of solid iron and nickel. The composition of the core is iron and nickel. All right, iron and nickel. But whereas the core, the outer core is liquid, the inner core is solid. All right. And the mantle is not molten. It is solid, but it is capable of flowing slowly over time. All right. It's capable of moving or flowing slowly over time. All right. So between the crust and then the mantle, there is a separation. The separation between the crust and the mantle is like taking, when you take maybe an egg, and you boil the egg, right? And you peel, you remove the shell. You see, there's a separation between the shell and then the albumen that is now the solid white. Is that not it? So that separation between the crust and then the mantle. So when we compare this to an egg, the crust is therefore like the eggshell, right? Then the mantle will be the albumen, the egg whites, and then the yolk will be the core, right? So when you boil it, those three layers, it's similar. So you see that the crust is just like your eggshell, it's very thin, and the mantle is thick, much thicker than then the yolk in the center. All right. So between the crust and then the mantle, we have a brick or a separation, and we call that the moho, or the Mohorovičić discontinuity, the moho. That's between the crust and the mantle. All right. Between the crust and the mantle, we have the moho. So the crust is the one we also divided into the oceanic crust and then the continental crust. All right. And then the inner core is solid, but the outer core is what? Liquid. But both the inner core and the outer core are made up of iron and nickel. All right, iron and nickel. So when we take the lower part of the crust and the uppermost part of the mantle, the two together are called the lithosphere. The lithosphere. The lower part of the crust and the upper part of the mantle, the two together are called the lithosphere. All right, the lithosphere. So therefore, we can say confidently that the asthenosphere, which is a layer below the uppermost mantle, just below the lithosphere, asthenosphere is very hot. It is part of the mantle. It is very hot, weak, and plastic. So this asthenosphere is very hot, weak, and plastic. And because of that, it is capable of flowing. Asthenosphere is very hot, weak, and plastic. All right. And so the crust ends up floating on this asthenosphere. All right. So we have the crust, the mantle, and the core. The crust can be divided into two: the oceanic crust and then the continental crust. All right. And then again, we could also beneath the crust, we have the mantle. But when we take the lower part of the crust and we combine it with the upper part of the mantle, then we have the lithosphere. Beneath the lithosphere, we have the asthenosphere, which is hot and weak, hot and weak. All right, hot and weak and plastic. Outer core is liquid, the inner core is solid. But both the outer core and the inner core are made up of iron and nickel. All right. So, like I said, the gap between the crust and the mantle is called the moho, the Mohorovičić discontinuity. And we are able to tell this through geophysics. Like we pass various waves down the earth, and then we are able to get that there is some separation or a difference in material properties at that level. All right. So in terms of that is the compositional layers. We can look at the layers in terms of physical properties and then chemical composition. So as far as the physical properties are concerned, of course, we know we have the atmosphere, then we have the hydrosphere. Then when we go down, we have the asthenosphere. All right, lithosphere, we know it's a specific layer we are calling the lithosphere between the lower crust and then the upper mantle. All right, beneath that, in the mantle, we have the mesosphere. All right, which is more or less the mantle. And then the outer core, and which is liquid, and the inner core is solid. When we go to the chemical compositions, it means now we are looking at the density. So we know that the crust, all right, when we talk about the crust, is lesser in density compared to the mantle. The mantle is higher in density compared to the crust, right? But the highest densities are in the core, And then the mantle has dark colored minerals. It's essentially mafic, right? Mafic. All right. And then don't forget, we equally said that the oceanic crust is denser compared to the continental crust. All right. All right. So We already discussed the fact that we have the continental crust and the oceanic crust. And the oceanic crust goes to about 5 to 6 kilometers thick. The continental crust, of course, is much thicker than that. All right. So the oceanic crust is dark colored, made up of dark igneous rock, which is called basalt. So this is typically very dark, and the geologic term for something that's very dark is mafic. So unlike the oceanic crust, which has a relatively homogeneous chemical composition, the continental crust consists of many rock types. And then the oceanic crust also has younger rock. That is, the ages of the rocks are much younger compared to the continental crust, all right? And the difference in the thickness and density between the continental crust and oceanic crust are responsible, all right, for the existence of ocean basins due to what we call isostatic balance. All right, so isostatic balance is a force of equilibrium between the how do you call it, the crust, all right, the crust, and then the mantle or the asthenosphere. It's just a balance, all right, it's just a balance. And that's such that when we have an erosion of a mountain somewhere, then it's going to be compensated by a rise of magma in another part. So the isostatic balance is a force of equilibrium, all right? It's a force of equilibrium, all right? So we said the oceanic crust has relatively homogeneous chemical composition. That is, the material properties do not vary too much, but the continent has a lot of many rock types, all right? And then the oceanic crust is younger than the continental crust and also has a higher density compared to the continental crust. Then the mantle, we need to know that the mantle is not molten. So the mantle is not liquid, all right? The mantle is not molten. It is solid. It is made up of high density ultramafic, meaning very dark rocks, silicate rocks, but it is capable of flowing when we subject it to a long amount of stress. And it takes more than 80% of the Earth's volume, all right? So the mantle is very thick. The upper mantle is divided into two parts. The top part forms a part of the lithosphere, right? When we combine that with the lower part of the crust, so we have the lithosphere. Can you see that? The lithosphere. Beneath the lithosphere, we have the asthenosphere, which we said is very hot and plastic and weak. All right, very hot and plastic and weak. That is the asthenosphere. So that is what we need to know about the mantle. All right. Then we can talk about the core, which we said is predominantly made up of iron and nickel with some trace amounts of oxygen, silicon, and sulfur. The outer core, like we said, is liquid, whilst the inner core is solid. And despite its high temperature, the inner core is very solid, all right? And it is very solid because it doesn't flow, and that is due to the immense pressures that exist in the center of the planet. Because ordinarily, we know that the temperature at the core, or in the middle of the core, is about 4,500 degrees Celsius. At that temperature, we should expect the material to be liquid, but it is not because of the immense pressures acting there. So this is the idea that we are able to get we are able to understand these various boundaries from geophysics, all right? That is by passing waves down the Earth. All right, so these compositional layers have sharp or abrupt boundaries between them. And so we are able to have a fair idea of the various compositions and the nature of the materials we are likely going to have. Even though we have not physically gone to the core or the mantle, we are able to tell the compositions. All right. Now, we also know that the outer core is liquid, and the iron and the nickel are moving. All right, there's some convection currents. So motion of the liquid iron and nickel in the outer core gives the Earth a dipole magnetic field. All right, a dipole magnetic field. And this is nearly aligned with the rotational axis of the planet. And this magnetic field, because of this, the Earth, the whole planet acts at how do you call it? As a magnetic field around the Earth. So the magnetic field around the Earth more or less originates from the outer mantle. All right. The magnetic field around the Earth originates from the outer mantle. All right. So the magnetic field reverses sometimes. So the reversal, in other words, when we say the magnetic field reverses, it means that in that case, the north is becoming south and south is becoming north. All right, it could reverse. And over the last several million years, the average time between reversals has been about 200,000 years. All right, 200,000 years. That's the average time between one reversal. And the last reversal took place about 730,000 years ago. So imagine the position of the north changes when we talk about a reversal. All right. And then a reversal can take less than about 5,000 years to occur. All right. So that is the whole idea about the magnetic field and the fact that we can have a reversal such that the position of the magnetic north varies over millions of years or hundreds of thousands of years. All right. The magnetic north is not always at the magnetic north, it varies. Is that clear? All right. So now we are done with the compositional layers. We could begin to look at the mechanical layers. The Earth has 5 mechanical layers: the lithosphere, the asthenosphere, which we said is beneath the lithosphere, right? Then the lower mantle, or which we also call the mesosphere, the outer core, and then the inner core. All right. So when we talk about the compositional layers, we only have essentially, we can talk about the 3 main layers: the crusts, the mantle, and then the core. But when we talk about the mechanical layers, we are dealing with 5. The Earth has 5 mechanical layers: the lithosphere, the asthenosphere, the lower mantle, the outer core, and then the inner core. All right. So geological processes, we can classify them into 2. We have the surface processes. That's the external processes, which primarily are controlled by the sun, the heat engine, external heat engine, the sun. And then we have internal processes. So internal processes are primarily controlled by various energy sources. And there are 2 main energy sources for this. The first is radioactive decay. All right, so radioactivity, all right, is the main of the primary source of heat energy within the Earth. All right, that's the internal heat engine from the decay of naturally radioactive elements like uranium, thorium, and potassium. All right. And then, so when we have like earthquakes and all that, crystal growth, they all give us examples of these internal processes. All right. And then we could also look at energy that came from when our planets formed, the remaining energy. So we know that during the initial formation of our planets, a lot of heat was accumulated. But as the planets cooled, the Earth gradually cooled, right? But then we have some remaining heat from when the planets formed. there is some remaining heat, the leftover heat energy from the formation of the Earth. We call that the primordial heat. Primordial heat. So the two main energy sources that powers the internal processes are in roughly equal amounts: the radiogenic heat coming from radioactivity, and then the primordial heat, which is coming from the heat that was left over during the formation of the planet Earth. All right, during the formation of the planet Earth. All right. So Earth's internal heat powers most of the geological processes and drives plate tectonics, which is a topic we'll be looking at. And it is important to know that although we have a lot of heat energy within the Earth, most of the energy sources, all right, the greatest energy source comes from solar energy. So solar energy is produces about 173,000 terawatt, all right. But then we see that the Earth's interior does not produce as much, all right, does not produce as much, because it's actually only produce about 3% of 1% of Earth's total energy budget. So the heat energy coming from the sun is much, much, much greater compared to the kind of heat energy we see from the within the Earth. All right, within the Earth. All right. So we have various forms of energy on or within the Earth. So like the force of gravity, we do know that it's due to gravity, objects from higher elevations are going to fall to the ground, right, to lower elevations. Then, of course, we have heat energy. So that's energy due to the moving of atoms. We have chemical energy released by the breaking or forming of chemical bonds, radiant energy, like a light energy. So energy carried by electromagnetic waves, right? Then we also have energy stored or released when atoms are binded together. We call that atomic energy. Is that not it? Atomic energy. All right. So do we have any pieces of evidence that kind of lets us know that indeed we have a lot of internal heat in the Earth? Yes. We can talk about volcanic eruptions, right? Volcanoes are characterized by very, very high temperatures. We are talking about 1,200 degrees Celsius. You can imagine that amount of heat. So that tells you that we have a lot of heat beneath the Earth, right? Then we also have the occurrence of hot springs. Think about a swimming pool that is hot water. The water is naturally hot. Another name for hot springs is geyser. Geysers, all right? Geyser, Geyser, geyser. Geyser. So these springs are hot because the water is coming about 2 kilometers from within the Earth, and this water is coming from a region that is extremely close to a magma. All right, so the magma is hitting the water before it gets to the surface. So we have naturally hot springs, and in some countries, if it can be tapped, it's a good source of energy. You can channel this directly into your washrooms and to provide naturally hot water for domestic uses, for bathing and all that, right? So that's a geyser, or for heating of homes. So occurrence of hot springs. Then global plate tectonics, we know that the movement of our tectonic plates or lithospheric plates is due to you need energy to cause movements of these huge plates, right? Then, of course, this movement of the plates produces earthquakes, and all that's pieces of evidence that show us that indeed we have a lot of heat energy within the Earth. Then mines and deep boreholes, the amount of heat at those depths tells us that indeed the Earth is very hot or has heat energy sources. So there are two main sources of geothermal energy: heat, geo from Earth, thermal from heat. Is that not it? So the Earth heat energy, geothermal energy. And when we talk about these two sources, the first one is, like we said, from radioactivity. Is that not it? Radioactivity. And then the other one is, how do you call it? The energy, the one we call the primordial, right? From accretion. So part of this particular energy is due to the slow cooling of the air from an earlier hotter state by accretion. All right, by accretion, the slow cooling of the earth from an earlier hotter state. So by accretion. So what is accretion? So accretion is the progressive coming together of particles by self-gravitation. The progressive coming together or coalition and coalescence of particles by self-gravitation. So it means that we have this gravitational collapse joining the particles together, right? You remember from your nebula hypothesis. And this released energy that heated up the earth, all right? So that's by accretion. And then the second one is radioactivity. So we know radioactive decay causes a lot of heat energy to be dissipated through the emission of alpha and beta particles and gamma rays. All right. So those are the two main sources of geothermal energy. All right. But the main two sources of energy, more or less, that powers the processes within the earth are the primordial, that's the one from the early states, which can be connected with accretion, and then radioactivity or radiogenic heat. So now we want to talk about something interesting called ion catastrophe. Ion catastrophe. All right. We do know that at some point in the time, in the formation of the Earth, radioactive heating resulted in temperatures that exceeded the melting point for iron, right? Now, if temperature exceeds melting point of a particular element, what happens? I believe when you know that when temperature exceeds the melting point of a particular element, we are going to have melting, correct? We are going to have melting. Is that not it? Melting. All right. So in the course of the Earth's history, we had this point where in the early stages, where the temperatures were so hot that they exceeded the melting points for iron. We are focused on iron, right? We are focused on iron. So once the temperatures were high enough for iron to melt, what happened? What happened? The iron will melt, right? The iron will melt. So once this iron began to melt, ion catastrophe happened. So as the iron began to melt, high density iron rich liquids began to sink towards the center of the earth, and then lower density liquids rose towards the surface. So what we are trying to say is that when this melting was happening, iron is very heavy, right? So the liquid, the iron rich liquid, is very dense, so it's sinking to the bottom. And then the lower density materials or various elements, materials with lower density, were rising towards the top. All right. And as the denser material sank toward the center, more energy was released in the form of heat energy. And this caused the temperatures to increase even more. And when the temperature increased more melting occurred, and more iron went down. The process where we had denser and denser bodies, all right, the heaviest elements at the bottom, followed by the next one and the next one and the next one till we get to the surface. So meaning at the surface, we have elements or materials with the least density generally, all right? And this particular process is called differentiation. So the planets began to differentiate into a density stratified body. All right. It began to differentiate into a density stratified body. In other words, at the bottom, we had a lot of heavier materials, and then towards the top, we had the lighter materials. And this is the reason for which we have the core made up of predominantly 90% iron and 10% nickel, because of ion catastrophe. All right, because of ion catastrophe. All right. So what can we say about ion catastrophe? Another profound result of this particular ion catastrophe was the initial formation of the primitive atmosphere, hydrosphere, and then the very hot planetary interior. All right, the very hot planetary interior. So that is ion catastrophe. It simply means that at a time during the formation of the Earth, temperatures became very hot or very high. And at this very hot or high temperatures, the melting point of iron was exceeded. And when that happened, iron began to melt and sink towards the bottom. So when iron sank towards the bottom, the elements or materials that they had a lower density, they came up. And the more this happened, the more heat was generated and the more iron melted, such that the heavier elements sank to the bottom, followed by the next and the next and the next. So we came to the surface. And because of this, we have a lot and a lot of iron in the Earth's core. All right, so that is ion catastrophe. All right, so heat flow in the Earth, we already know about convection, and we know conduction. Is that not it? Then there's another form called advection. Advection. All right. So heat flow by convection, heat flow by advection. All right, and the other flow is by what? Convection, convection and advection, and then conduction. All right, these are the three main means of heat flow. All right, heat flow. All right. So are there any questions on any of this? Are there any questions? All right, so then we can continue. Yeah, so yes, radiation, but the principal modes of transport are the three we mentioned, all right? The three we mentioned, conduction, all right, conduction, because we have a, you know, for you to have radiation, it means you should have what? When you have two particles in contact, we don't have radiation, is that not it? So essentially, we are dealing with this part, materials are in contact within the Earth's crust. So we are dealing with convection, conduction, and then advection. Is that clear? All right. So those are the three means. All right. So yeah, when we talk about advection, it means that we have the particles, all right, the particles that are moving, that are being transported with the fluid. All right. Here we are talking about particles being transported. You understand? That is advection. That's the difference. That's the difference. All right. So advection is referring to the transport of a substance or by the flow of the liquid. All right, the transport of a substance. All right. So it's a little different from convection. All right, or conduction. So you can look that up for further explanation. All right. All right. So now we want to talk about geothermal gradients. We know that the higher you go, the cooler it becomes, right? Similarly, the deeper you go, the hotter it becomes, all right? So geothermal gradient is the rate of increasing temperature with respect to increasing depth in the Earth's interior. So from shallow depths to about 61 meters below the surface, the temperature is constant, all right? But then when we get to about 1 to 2 meters, the gradient is different, it varies, because it is affected by atmospheric changes, and then water is also in the ground, in the rocks. We call that groundwater, right? So, but once we exceed these depths, then we see that the rate of change is quite constant at about 25 degrees Celsius in most parts of the world. So the rate of increasing temperature with respect to increasing depth is what we call geothermal gradients. All right, geothermal gradients. Very close to magmatic sources, the gradients can go as much as 200 degrees Celsius per kilometers. It means when you travel down for every kilometer, you have a change of temperature of 200 degrees, right? But generally, we said 25 degrees is quite normal as the geothermal per kilometer as the geothermal gradient. And where we don't have a lot of tectonic activity, that is in tectonically stable zones, we find out that this average gradient varies between 15 degrees and 30 degrees Celsius. All right. The rate of change of temperature with depth, that's what we call geothermal gradient. So we know that at the center of the Earth, which has reached 4,500 degrees Celsius, and then near the surface of the Earth, the rate of increase in temperature, thermal gradient ranges from 15 to about 35, all right, or 15 to 30. Any of them will be fine, around that range, all right? And we do know that when we are dealing with tectonically active zones, the temperature variation is different, up to about 200 kilometers degrees Celsius per kilometer. But in places that do not have this much tectonic activities, about 15 to 30 or 35 degrees Celsius per kilometer. So geothermal gradients is nothing but the rate of change of temperature as we go down the Earth. That is geothermal gradients, all right? Rate of increase in temperature within the Earth, with depth within the Earth. All right.